Good morning. So we have finished statistics and we've just got a little bit of mechanics to do, 2 weeks worth in fact, and then we're done with the whole of statistics and mechanics. And rather than going on to some year 2 stuff, I'm going to do a little bit of work on proof for the final 3 weeks of term. We're carrying on posting videos right till the end. And as I said to those of you I saw in school on Monday, if you've kept up with the videos, then we are ahead of where we would have been had the school stayed open. So we're in a really privileged position, provided we keep up. And the great thing about the videos on YouTube is that they're there. So if you haven't caught up, you've got the whole summer to do so. Please take that on board. Anyway, I'm going to start by taking a step back to something you've done before in mechanics, and that's velocity time graphs. In fact, this was at GCSE as well. If we've got a graph that describes the velocity of something, not the distance, not a distance time graph, a velocity time graph, you may remember that the acceleration of whatever it is that's travelling is found by working out the gradient of the lines, and the displacement, the distance travelled, is found by working out the area under the line. And you may remember answering questions like this. So I think it's good just to start by having a go at page 135, question 3. The acceleration of the cyclist in the first 20 seconds, so that's the gradient of this line. And the deceleration, that's the gradient of this line, so that'll be negative. And the displacement after 75 seconds, well, that's the area under that shape in total. And when you've had a go at that one, page 136, question 7, very similar, but you've got a missing value. So they tell you how far it travels in total, and you've got to use that to work out the missing value. Right, so I'm going to pause at this point. I'm going to do those questions. You do those questions. I'll see you again in a minute. So here is the first one, the acceleration in this bit. Well, you had to remember how to work out gradient. It's the y divided by the x. So that was 0.4 meters per second squared. It doesn't matter whether you write it as that or that, means the same thing. Then deceleration, so it was this section here. So that was 8 and that was 15, 8 and 15, y divided by x. And it's downhill, so it's negative. And I would type that into my calculator, but it's a horrible decimal, so I left it as minus 8 over 15. It's actually minus 0.53 recurring. If you round it to 3 significant figures and get 0.533, that's also fine. And then the displacement is the area under the curve. Now, you could have done it as a triangle, a rectangle, and another triangle. But if you can remember the trapezium formula, it's a whole lot quicker. So the trapezium formula, you've got your two parallel sides, which in this case are 40 and 75. The height is 8, so it's a plus b over 2, the average of those two lengths, multiplied by how far apart they are. So that gave you 460. And the second one I asked you to do was a little bit fiddlier, but hopefully you were okay. The key was realising that they told you that the journey was 100 metres. So this whole area is 100 metres. So I worked out the two bits that were easy. So the rectangle is 70 and the triangle is 10. So that makes 80 metres. So I knew that this area here had to be 20 metres. And I drew that bit down here. And this is another trapezium, although it's one that's twisted from the previous one. So this length is the one I'm trying to work out, u. I know this length is 10, that's there. And I know that they are 3 apart. So a plus b over 2 times 3 is 20, has to be 20, the area has to be 20. So I just did a little bit of algebra here. I divided both sides by 3, multiplied both sides by 2, and then took away 10, and it was easier for me to leave that as a fraction. That's 3 1/3, isn't it? You then had to work out the acceleration for this section here. Well, I now know that that's 3 1/3, So this distance here is 10 minus 10 over 3, 10 minus 3 and a third, which gives me 20 over 3. So that's how far up it went. It went across 3, so that gives you your acceleration, 20 over 9 meters per second squared. Now that's all a little bit too convenient, because in the real world things don't accelerate constantly and then hold their speed exactly and then decelerate constantly. In the real world things change, don't they? So more often than not, when you're looking at the velocity of something, it's probably going to look more like this or more like this. And that means that we're dealing with variable velocity and, more importantly, variable acceleration. And some of you who do physics will understand the significance of variable acceleration. As soon as acceleration starts to vary, you can no longer use your Suvat equations. So when we're dealing with variable acceleration, where here the acceleration, the steepness of the curve is 0 and here it's quite steep, or deceleration, where here the steepness of the curve is quite steep, so it's accelerating fast, but then it slows to 0 acceleration, we can't use these simple techniques to work out acceleration and displacement. If only we had a way of working out the gradient of a curve or the area under a curve. Well, of course we do, don't we? We've got differentiation, which allows us to work out the gradient of a curve. So if I want to work out the acceleration from a velocity graph, I need to do some differentiation. And if I want to find the area under a velocity graph, which is what gives me the displacement, well, that's integration. And differentiation and integration are inverse processes. So if I know displacement and want to work out velocity, then that's a differentiation. And if I know acceleration and want to work out velocity, then that's an integration. And so variable acceleration can be described with an acceleration formula, a equals something. It can be described with a velocity formula, v equals something. And it can be described with a displacement formula. I don't know what letter you want to use for displacement, S, X, whatever. And if we're given one, then we can use differentiation and integration to work out the other two. And that's how we solve problems about what's the acceleration and what's the displacement when we've got a varying situation. Here, nothing, well, the speed was varying, but we had constant acceleration, and we could therefore say, right, gradient, we can work it out to work out the acceleration, area under gives us the displacement. With these sorts of situations, it becomes an integration and a differentiation problem. So tomorrow we're going to get into the whole differentiation integration thing first, but let's firstly do a question which just introduces the idea of describing either acceleration, velocity or displacement with an equation rather than with a graph. Okay, so firstly I apologise for the dreadful text quality here, I don't know what happened there, but here we've got the movement of a body described in terms of a velocity equation. So v equals something to do with t. T will always be the variable in these questions, but sometimes we get a equals, it describes acceleration, and sometimes we get s, or another letter to stand for displacement, equals. But in this question we're given the velocity. And we should be able to do all of this question without having to get into differentiation and integration. As I said, that's tomorrow. So the initial velocity, well, that's what you get when t is 0. So when t is 0, I know that if I work that out, I'll get 2 lots of 0 squared, take away 16 lots of 0 plus 24. So v equals 24. meters per second. And I'm going to pause at that point because what sort of graph have I got here? Well, hopefully you recognise it's a quadratic, and it's a happy quadratic, plus x squared, or in this case t squared. So I know that it's going to be this sort of shape, and I already know that it starts on the x-axis at 24. So I'm going to start building up a picture. Sorry, it starts on the y-axis at 24. When t is 0, so that's not the x-axis, that's the t-axis, the velocity will be 24. So there we go. I've made a start at my graph. The values of t when the body is instantaneously at rest. Well, what is your velocity when you are at rest? Hopefully you can see that that's when v equals 0. So if I make this equal to 0, we're solving a quadratic equation, aren't we? And it's perfectly acceptable to use your calculator to do that. However, just to keep my skills honed, I'm dividing everything by 2 there, and I'm hoping that I can make a 12. Yep, I can. So that's going to be t, I'll move this down, t minus 6 and t minus 2. So 6 and 2 are the 2 places where it is instantaneously at rest. Could have done that on the calculator. There's absolutely nothing wrong with that. Now, just going to get my units straight. So velocity is in meters per second, so I know that time will be in seconds. So I know that this curve is going to go through 0 at 2 and 6 seconds. So clearly these axes are not to scale. Now remember what I said about, I know the shape of the graph, so I'm in a pretty good position now. I know it goes through here on my velocity axis, and I know it goes through my time axis there, so I'm going to say, right, and I'm going to make a confession at this point. I didn't realise for several years that the turning point, and we can find the turning point in a number of ways by completing the square specifically, but it's always going to be halfway between your roots. So I now know that the bottom of that curve will be at 4 seconds. And so another way of working out how low that is to plug t is 4 into the original equation when asked to do that, but that's part of it. Okay, so part C, we're asked what's the value of t when the velocity is 64? Well, what I did here was I asked when is v equal to 0. So now I'm going to ask when is v equal to 64? And because I only solve quadratic equations when I have a 0 on the right hand side, I've got that. And again, I could do this on my calculator, or I could use another method. I think that's going to be minus 10 and plus 2. So the two solutions are going to be t equals 10 and t equals minus 2. Well, we're told quite clearly in the question, surprise, surprise, that time's got to be positive. You can't have negative time. So the answer to the question is that the velocity will equal 64 meters per second after 10 seconds. And again, that's sort of confirmed by my graph, because my graph, the velocity is heading up, and yeah, at 10 seconds you can imagine it would have reached 64. Now if you look at question 10, the greatest speed of the body in the interval 0 to 5, so this is 5 seconds here. Okay, my graph isn't particularly up to scale, but the greatest speed between 0 and 5, well, that's here, isn't it? So for D, the greatest speed is 24 meters per second, and that's the initial speed. In that first 5 seconds, that's the fastest speed that it gets. Now I'm going to stop at that point and just plot this on my calculator, just so I can be sure that I haven't made a mistake and slipped up. So I am going to go to graph mode. I'm going to delete a function that I was doing yesterday, and although this is v equals something to do with t, the calculator only works in terms of y and x, but that's fine. So I'm going to type in 2x squared, not 2t squared, minus 16x plus 24. I'm going to draw it. Haven't really given much thought to the axes yet, have I? So if I have a look at these axes, I say, right, okay, if I go to V window, my x-axis, well, let's go from 0 to, I don't know, 8. So I'm going to go from 0 to 8. The scale of 1 just means how often do they put the tick mark, so that's fine. And the y-axis, well, if I go from 0 up to, well, actually 25 is pretty sensible. I might go a bit further. I might go as far as 40. And then when I do exit from that, annoyingly it takes you back to that window, so I then have to go back to draw. And yeah, that looks like I expected it to look. And if I press my favourite button on the calculator, G-solve, I can just confirm the y-intercept, which I'm expecting to be 24. Yep, 24. And I never know how to get out of that. I think if you press G-solve again, there you go. And these 2 points here, they're referred to as roots, aren't they? The place where it crosses the x-axis, so that's root. And I'm told that I've got 1 when x is 2, and if I press xe again, it finds... Sorry, I don't press xe, I press the right cursor. There we go, I've got another when x is 6. So I've confirmed what my graph showed me. You can't use your graphical calculator to solve the problems. You've got to do it the old-fashioned way, because not everyone's got a graphical calculator. But because we're lucky enough to have one, we can check. So there's no way we should get this wrong, but we're only allowed to use it to check rather than to actually solve it in the first place. So I am on page 184 in the Statistics Mechanics textbook, and there's 2 questions that I would like you to have a look at. They both feature movement described as a V equals equation. So question 5 and question 6. They are very similar to the example question that we've just done, and you should be able to answer all of the questions without differentiating or integrating. It's just using the quadratic skills that we've spoken about. I will make one comment. Question 5, the formula is 3t squared, so I know that that is a happy parabola, so that's like the one we've just done. Question 6 is far more realistic because we've got an unhappy quadratic, so I know that's going to be an upside down parabola, and that's what we expect because when things are fired, they move in that projectile motion, don't they? The upside down parabola. So on page 184, have a go at question 5 and question 6. And then tomorrow we'll get into a little bit of differentiation and integration applied to this problem.